Hello friends, I am Amir Manazami and today we are going to study free vibrations of viscous damped single degree of freedom system part 2, because last time in continuation with the last lecture we have studied this topic but only for the first cases, which was under damped case. So now we will study the critical damped case and over damped case. So we will have just a quick review that we were studying. The equation was mu double dot plus cu dot plus k of u was equals to 0. So no external force was acting, so therefore it was free vibration cases, but c was there, so this is the damped case. So we are telling free vibration of viscous damped single degree of freedom system. So we have find the equations for it and we solved this. So finally we got two roots, and the roots were s1, which was minus xi of omega n plus under root xi square minus 1 omega n, and the second roots s2 was minus xi omega n minus under root xi square minus 1 into omega n. So case 1 we have studied, case 1 which was under damped case, under damped case. So where xi was greater than 0 but less than 1. So we can see if xi is greater than 0 and less than 1, and if we will put the values here, so this would be inside root would be a negative, so means an imaginary value would be there. So we got two roots, and those roots were minus xi omega n plus iota into omega d, and the second roots was minus xi omega n minus iota omega d, where iota is the imaginary number whose value is under root minus 1, and omega d was a damped natural frequency, that was omega n into under root 1 minus xi square. So these two values we have studied in the last class. So now we will study the second case today. So case 2 will come to critical damping. Critical damping. Okay. So when we state it is a critical damping when xi is equals to 1. Okay. So now our first root would be equals to, we will put the value here 1, so it would be minus of omega n, and 1 minus 1 0, so it would be 0. So first root would be minus omega n and s2 would be minus omega n. So both roots s1 is equals to s2. So therefore we know the solution for this. So homogeneous solution for the two identical real roots. So what would be the solution for it? We are having c1 e to the power minus omega nt plus c2, and have same roots, so there would be a multiplication with the independent variables t multiplied by e to the power minus omega n t. So this is the solution. So now what we will do, we will just find c1 and c2. So we will write here again u of h is c1 e to the power minus omega n t plus c2 t into e to the power minus, sorry, xi is 1 here, so therefore we will have only omega nt, and u dot, if you want to find u dot of h, that would be equals to, we will just differentiate it, so minus omega n c1 e to the power minus omega nt plus, now C2 is a constant, we will take it outside and we will differentiate uv. So u, let t be there and differentiate it, minus omega n e to the power minus omega nt plus v. So we will differentiate e to the power minus omega nt would be u now, and t would be 1. So we will solve it, minus omega n c1 e to the power minus omega nt plus c2t, and it would also become minus, so c2t e to the power minus omega nt plus c2 e to the power minus omega nt. So we will have this e to the power minus omega nt common, c2 and c2 is there, so we will have this equation c1. So we can write finally this equation e to the power minus xi omega nt would be constant, so xi is 1 here, so we'll take it outside, and 1 minus omega nt omega n into t, and we have differentiated here would be c2 omega n is here, so omega nt into c2 minus omega n c1. Okay, now we will have the initial conditions that u at t is equals to 0 would be u naught, and u dot at t equals to 0 would be equals to u dot naught. So these are the initial conditions given, it may be 0, 1, anything. So we will put the value in the equation, let it equation 1 and let this be equation 2. So we will substitute this value, that u at t equals to 0 equals to u naught would be equals to c1 e to the power t0, that would be 1, so c1, and c2 t, so t would be 0, so these would be 0, so c1, this implies that c1 is equals to u naught. And similarly we will put in the second equation, u dot t equals to 0 would be u naught dot equals to, we'll put here t equals to 0, it would be 1 minus omega n into t, so 1 minus, that would be c2 minus omega n c1 minus omega n, and c1 we know that is u naught. This implies that c2 would be equals to u naught dot plus omega n into u naught. So we found c2 also. So therefore the final solution we can have this final solution as u of h is equals to c1 is u naught, so u naught into e to the power minus omega nt plus c2 is u naught dot plus omega n into u naught multiplied by t into e to the power minus omega n into t. So finally we will have this solution for the critical damped case. Okay, now we will have the third case, case 3. which is overdamped case. Overdamped case where xi is greater than 1. So we were having two roots initially from the basic formula, which was minus xi omega n plus under root xi square minus 1 into omega n, and the second roots were s2 minus xi omega n minus under root xi square minus 1 into omega n. Now xi is greater than 1, so therefore this value would be real. So two real and two real roots would be there. So u, we can also write here, just a minute, we can have this value as minus xi omega n plus this we can write as omega star, where omega n into xi square minus 1, and s2 we can write here as psi omega n minus omega star, where omega star is omega n into under root xi square minus 1. So it is different from omega d, where last cases we have considered omega n into under root 1 minus xi square was omega d, but we are taking omega star as omega n into xi square minus 1. So for simplicity we have just write with this notation. So now we will have the solution, and we are having u of ht is equals to e to the power minus of xi omega nt a1 into cos hyperbolic omega star t plus a2 sine of hyperbolic omega star into t. So here it is cos hyperbolic omega star t and a2 sine hyperbolic omega star t. And we will have, if we will differentiate it, so we'll get also the value to it, and finally I will put the value. So u naught dot 0 equals to u naught dot, initial conditions are given, initial conditions, and u at t equals to 0 would be u naught. So we will put the value here. So finally we will get the solution uh as e to the power minus of xi omega n t into u naught cos of hyperbolic omega star t plus u naught dot plus xi omega n into u naught upon omega star into sine hyperbolic omega star into t. So this is our solution for the third case, which is overdamped cases. So we have seen all the three solutions, so we will summarize here. So case 1 was underdamped case, where xi was 0 to 1, and we were having the solution, homogeneous solution, as u of h equals to e to the power minus xi omega n t into u naught cos omega dt plus u naught dot plus xi omega n u naught upon omega d into sine of omega dt. This was our case 1. Now case 2, where critically damped where xi equals to 1, and we get homogeneous solution or general solution as u of h is equals to e to the power minus xi omega n t, and xi here was 1, so therefore we can replace it xi, so minus of omega n t into u naught 1 plus omega n into t plus u naught dot into t. So this was the second case. In case 3, we are having over damped, which is xi is greater than 1. So we will have u of h would be equals to e to the power minus xi omega nt t into u naught cos of hyperbolic omega star t plus u naught dot plus xi omega n u naught upon omega star into sine of hyperbolic omega star t. So omega star t. So all the 3 cases are here with us. So 3 different cases: underdamped, critically damped, and overdamped case for the free vibration. So we will now code in the Matlab. So let's code it. So we will just go to Matlab and we will have first clear all. Okay, so we will see the workspace also. This is clear. Now we'll see how to write the code. So we are having the formula that mu double dot plus u dot plus ku equals to, here it is written in this manner, but we will have f naught would be 0, so therefore right hand side would be 0 for us, or we can say right now our case is equal 0, so it is our, we can say, free vibration case. Free vibration viscous damped case, okay, where homogeneous solution is possible. So what are the input required? So we know that we have xi value input, and right hand side, hence f naught would be 0 here. We have mu double dot, so there must be the value of m, so we have considered m as 1 here, and time period, so that would be equals to 1, and natural frequency is just the formula 2 pi by t, so we will have omega n, and we know k, that is the stiffness, so that is m into m omega n square, so we have write it in this manner, and omega f equals to 3, which is the forcing frequency. So right now we are not related with it, so we'll not use. Yeah, omega star, omega st is the omega star. Omega n star we have considered, that is omega n into under root 1 minus xi square. And initial conditions we have written u naught at t equals to 0, so u naught equals to 1 and v naught equals to 1. So but these value we have considered because in displacement vector format, so it would be the first value, so so that we have considered u of 1 equals to u naught and v of 1 would be equals to v naught. Now eta, what we have considered as omega f upon omega n, so it would be useful for the second case we will study right now. And this is the time duration, so this t is the time duration, which is different from the time period. That was this t, capital T, this was the time period. We know we can write here as time period, and this t here is the duration, so it is duration. Okay, now omega d is omega n square root, means under root of 1 minus xi square, and we have just written sq as short of this value, and we have homogeneous solution, and we will just feed here at zeros of length of t comma 1, that would be in the vector format. So now we will write the code. We are writing for the value I equals to 1 to length of the t, and we are having the constant ep, which is exponential of minus xi omega n t, and si would be sine of omega d into t, and cos co is the cos of omega d into t. Similarly, sine hyperbolic case would be there, so sine hyperbolic we have written in this manner, cos hyperbolic, and it will be the particular solution which is not useful here, so we will not taking count it. So u of, if the case 1 here, it is the, you can write here as case 1. What was the case 1 here? Xi is greater than 0 and less than 1, so it is under damped vibration. Similarly, if xi is equal to 1, we will say it is critically damped. And we know if xi is greater than 1, we can write it as overdamped. And another case which we have not taken into account, but we know that if xi is 0, so we know that we'll write case 4 we have taken undamped, where is there is no damping. Okay, xi is 0 here. Case 3, and it is case 2. And we will end all the if else condition, because we have written here if the first case is xi greater than 0 and less than 1, so our solution is this. And else if xi equal to 1, which is critically damped, then our solution would be here it. And if xi is greater than 1, then our solution would be this, and we have already studied this part, just we have written in the code. And the fourth case we have taken that if xi value is 0, so we know that xi value is 0, we will put the value 0, so we will get this value. Now we will end the loop and we will just see. So it would be the particular solution which we are not studied, which is 0 here, because right hand side is 0. So ut would be equals to u of h, and our figure would be plotted here. So we will just see. So we are interested in only u of h, so we can just lock it, and now we will see. We'll just run the program. So we are interested in the first case right now, so we will see 0.02, which is undamped, less than 1 and greater than 0. So we will just and static force is 0, so therefore we will see. So this is the case for underdamped vibrations. So we can see it is the underdamped vibrations, that with duration it is getting diminished. Okay, so it is our underdamped cases. Now we will go for the second case. We will run it again, and if xi value is 1, so xi value is 1, so we will go for critical damping. So let's see, this is 0. So what, so we can see the vibration has already ceased, and at 1 we can see at this point almost, and it becomes 0 after that. So it got ceased at 1. So we can see in a large way. So this is the critical damped cases, where before 2 means almost at 1, it was just going to be ceased or 0. Now we will see the third case, and the third case is at xi equals to greater than 1. So we can put the value as 2. Let's see. So now we can see that after 2 it is getting diminished. Okay, so this is the overdamped cases here. So we have seen all the three cases, and one case here extra we have studied, where xi equals to 0, that would be undamped, so we will put xi equals to 0 and this equals to 0. So if there is no damping, then we know that the oscillation will continue, so there would be no damp at any duration, so it would be continuous forever. So damping help us to just diminish the oscillations. So these were our Matlab programming code for the above 3 or 4 cases which we have studied. So in the next class we will study the forced vibration case. Till now we have studied the free vibration damped viscous cases. So thank you.